Well, today I'm going to talk about stoichiometry. I suppose if I could think of one subject we're going to cover in chemistry this year that's the most important, it would be stoichiometry. It's a big word. What exactly does it mean? Stoichiometry means that when I set up a reaction, I have a recipe, I balance an equation. How do I know exactly how much product I'm going to get based on how many reactants that I've started with? We need to use all the skills that we've learned first semester, translating chemistry, making the correct formulas, balancing equations with coefficients, learning how to use molar masses and so forth to figure this out. It's a big subject. We're going to baby up on it. And I want to talk about only two things today in part one, which is mole to mole conversion, and we're also going to talk about mole to mass conversion. So let's get started on this. First thing I'd like to talk about is mole to mole conversion. Okay, let's suppose that I have a very simple reaction. This is you guys having lunch, right? You eat sugar, you breathe oxygen, and you produce carbon dioxide and water. Very, very simple. Well, here's the first thing we need to do before we get started on it. We always said it's all about moles, so let's go ahead and balance this equation here. Okay, let's take a look at it. Carbon, hydrogen, oxygen. We said we'd always do the carbon first, right? So let's do that. We have 6 carbons here. We've only got 1 over here. So let's put 6 in there, and I think I'm going to switch the color just so you can really see what I'm doing. Very good. Now we've got 12 hydrogens and 6 oxygens. Let's do the hydrogens next. 2 over here. We want 12, so let's times by 6 also. Not getting my red color there. Let's try that again. Okay. How about my oxygens? 6 times 2 is 12. 6 times 1 is 6. That gives me 18. Got 6 over here, so I need 12 over here. So we have to get another 6. So it's all 6s to balance this guy out. Okay. Now think about this as a recipe. Let me read it to you again. You take 1 mole of sugar and you add 6 moles of oxygen. And if the reaction goes all the way, that is, nobody's limiting, we should get 6 moles of carbon dioxide and 6 moles of water. So the ratios are 1 to 6 is 6 to 6. Okay, here's the question. Given that oxygen is unlimited, if I eat 10 moles of sugar, how much carbon dioxide gas do I fart? Okay. Now the important thing here is not the farting. The important thing is that oxygen is unlimited. Remember last time we talked about limiting reactions, and the whole point of that thing was you only get product determined by who the limiting reactant is. The other guy really doesn't matter. So, who is the limiting reactant here? Well, if oxygen is unlimited, we have tons of oxygen, right? We'll cross that out. So the limiting reactant here will be the sugar. That's the one that we're really interested in, the sugar. Okay, the amount of sugar here is going to determine the amount of carbon dioxide. Very good. Let's go ahead now and write it down. So, I'm going to bring up a text here, and let's put it in here. We are going to start off with 10 moles of sugar. Very good. Now, what is the mole ratio here? Well, the mole ratio, if you look at my recipe there, says that I get 6 moles of carbon dioxide for every 1 mole of sugar. 6 to 1. I get 6 from 1, right? And that is going to tell me how many moles of carbon dioxide I should get. Very good. So I get 6 moles from every 1 mole of sugar. That was the ratio. Pretty complicated math, huh? 10 times 6 is 60 divided by 1 means the answer is I get 60 moles of carbon dioxide. I only was able to get that ratio because I balanced this equation out. Okay. So far so good? Let's move on. How about another example here? Lead iodide plus potassium chloride equals lead chloride plus potassium iodide. Before we get to the question, let's automatically assume we got to balance this equation. Is it balanced? 1 lead, 2 iodides, 1 iodide. That's no good. Let's balance that guy. 2 potassiums. Oops. We need to have 2 potassiums up there. How are we doing? 2 chlorides, 2 chlorides. Looks good. So the molar ratio is 1 to 2 is to 1 to 2. The mole-to-mole ratio, right? We see that from the recipe. Now, here's the problem. Assuming that potassium chloride is unlimited, so that's not important, right? Let's go ahead and cross that out so we don't forget. This doesn't matter. That is not going to determine how much product I get. If that is unlimited and I have 10 moles of potassium iodide, how many moles do I get? Excuse me, 10 moles of lead iodide, how many moles of potassium iodide do I get? Let's go ahead and write that out there using our mole-to-mole conversions. So we start out with 10 moles of potassium iodide, right? And we're going to multiply that by the mole-to-mole ratio. What's the ratio? Well, I get 2 moles of potassium iodide. 2 moles of potassium iodide for every 1 mole, right? For every 1 mole of lead iodide. Let's bring that back here so you can see it a little better. Okay, very good. Complicated math. So if I have 10 moles of lead iodide and I get 2 for every 1 mole, 10 times 2 is 20, divided by 1 is still 20, and the answer is I get 20 moles of potassium iodide. Simple enough. Now I know most of you could probably just see that from the equation. You could see that 1 gives you 2, so we knew that already. But I want you to get in the habit of doing it this way because when we really learn all the pieces of stoichiometry, it's going to be important to have this step in there. Okay, let's move on. Now we're going to make it a little more complicated. So, when I set up a reaction, and I go out there and I say, well, we need to have 3 moles of something, it's really hard to weigh out 3 moles. You got to weigh out grams. You got to do mass. So I really have to deal with things in mass. And how do I get from moles to mass? Remember a long time ago we said you have to do the molar mass calculations for this. Okay, how about this one? Iron plus sulfur. That's kind of a weird sort of sulfur, solid sulfur, S8. Don't worry about that. Equals iron sulfide synthesis reaction, yeah? Start the way we always start. Let's balance this guy. 1 iron, good. 8 sulfurs, right? Ooh, so we need to have 8 of them over here. Let's put that in. Now I've got 8 irons, right? So let's go ahead and adjust the other side. Put an 8 over there. And I think I'm now balanced. Okay, so the ratios are 8 to 1 to 8. Let's go ahead and look at the problem. Given that you have 2 moles of sulfur and iron is unlimited. Iron is unlimited. Okay, so we don't care about the iron. Let's get rid of that. The amount of sulfur will determine the amount of product iron sulfate. So, given that iron is unlimited and you have 2 moles of sulfur, how many grams do you get? Not moles, but how many grams of iron sulfide do you produce? Same thing, except now we have an extra step here. Let's go ahead and start it out like we did before. 2 moles of sulfur times the molar ratio. What's the molar ratio? I get 8 moles of iron sulfide, right, for every 1 mole of sulfur, right? So let's go ahead and put that in here before we forget. 8 moles of product for every 1 mole of sulfur. Very good. Now if I go ahead and just times that there, let's go ahead and times it so it's not confusing, right? 2 times 8 is 16, divided by 1 is still 16, so I get 16 moles of iron sulfide. But that was not the question. The question was, how many grams do you get? So we need to do an extra step here, And remember, the way you convert moles to grams, mass, is by multiplying by the molar mass. You can do the calculation. I think most of you know how to figure out the molar mass of iron sulfide. Comes out to be 88 grams per mole, right? 88 grams per mole. Let's put that in here so we don't get confused. 88 grams per mole. Okay, so if we times by 88, 16 moles times 88 grams per mole is 1,408 grams. That's a lot of product, right? 2 steps, right? First step, use the mole-to-mole ratio that you've gotten in the balanced equation. Second step, convert the number of moles to grams by multiplying by the molar ratio, the molar mass. Let's try another one. Now here's an interesting one, conservation of mass. We've talked about this a lot, right? And this is good verification that what I'm doing is true. If I have balanced things correctly, and if stoichiometry is true, then we should have conservation of mass. That is, the mass of the reactants should equal the mass of the products. So in this one, I've already balanced it, right? 4 irons plus 3 oxygen molecules come together to make 2 molecules of iron oxide. Let's check out the molar masses and the weights. Now I've already done it for you here. The weight of iron is, I'll go ahead and circle this so you can all see what I'm talking about, is 55.85, and I have 4 moles of it, so that gives me 223.4 grams. Okay? The molar mass of oxygen, and most of you probably remember that one, is 32. You have 3 moles of it, so that should give you 96. And the last one here is our product, and our product, right, is iron oxide, which weighs 159.7. You have 2 moles of it up here, gives you 319.4. And I think you guys can see that if you add up your reactants here, you will see that these reactants, right, add up to 319.4. Reactants equal the same mass as products. Conservation of mass seems to work if we have a balanced equation. Well, you go ahead and try one. Check this one out. Now this is our classic equation. Every time we light up the Bunsen burner, right? Methane gas plus oxygen, combustion, right? One of our 5 reactions gives us water, carbon dioxide. It should work for this. If we have balanced equation, we should be getting conservation of mass. Let's start out like we always start, right? Let's balance this equation. 1 carbon, 1 carbon. 2 hydrogens, 4 hydrogens. Oops, that's no good. Let's go ahead and balance this guy by putting a 2 in there. Let's do the oxygens now. 2 times 1 is 2, and another 2 is 4. Oops, but we only have 2 there. So we need to have 4. And how am I doing? 1, 1, 2. I think I'm balanced. So the mole-to-mole ratios are 1 to 2 gives us 2 to 1. Fair enough. Here's my question for you. Make that a little bigger here. I don't know if you can see it. Let's choose a bigger font here. Okay. Balance this equation and convert to grams and check for conservation of mass. No problem. Let's go ahead and do it. Okay, I'm going to go ahead and write these in, but I hope that you guys remember how to do this, right? So, methane gas, right? Methane gas, CH4, is 12 plus 4. That should be 16, right? No problem. Oxygen. Now, oxygen, 2 oxygen is 32, right? But remember, you have 2 of them. So this really weighs 64 grams. Water. We always remember water. That's one I told you to remember all the time. That was 18. But you have 2 of them. So that means 2 times 18 was 36 grams. And carbon dioxide, you've only got 1 molecule of it. Carbon is 12. Oxygen is 16. So you have 2 oxygens, that's 32. Plus 16 means you have 44. I think you can see that 16 plus 64 in the reactants, surprise, surprise, equals 36 plus 44 grams in the products. I'm going to put grams there so we don't forget. This is mass. Conservation of mass holds if you correctly balance an equation. Okay, let's move on. How about this equation? In this example, we're taking solid lithium, diluting it in water. We get lithium hydroxide plus hydrogen gas. First of all, is this equation balanced? Let's take a look. 1 lithium, 1 lithium. Good. Let's do the oxygen next. 1, 1. Good. Hydrogen, 2, 2. Hey, did I get lucky? I think I did. No, I didn't. I've got 3 hydrogens over here, don't I? That doesn't work out. So let's go ahead and put a 2 in here. Now I've got 2 lithiums though, right? Let's put a 2 over here. 2 lithium. How about my hydrogens? 2 times 2, 4. Oops, need a 2 over here, don't I? And oxygens. 2 times 1, 2. There we go. That looks balanced. Okay, so the mole-to-mole ratios are 2 to 2, gives us 2 to 1. Given that you have 4 moles of lithium and unlimited water, so the water's unlimited, that doesn't matter. Okay, let's cross that out. We don't care about water. The amount of product will only be determined by the amount of lithium. And we have 4 moles of lithium. How many grams of hydrogen gas, then, do I get from the lithium? Very good. So we're starting with lithium, right? Let's go ahead and write that down. We start with 4 moles of lithium. Very good. Now we're going to times it by the mole-to-mole ratio we got in this recipe. The ratio is we get 1 mole of hydrogen gas, right? I'm going to see if I can put a subscript on this so you can really see it, right? 1 mole of hydrogen gas, and we get 1 mole of hydrogen gas from every 2 moles of lithium. See the 2 up here? So you get 1 of these from every 2 of these. Great. Let's times it. 4 times 1 is 4 divided by 2 means that I get 2 moles of hydrogen gas. Very, very good. Now let's do that trick here again on the subscript. That's great. But that was not the question. The question is, how many grams of hydrogen gas do you get? Okay, so we need to multiply this by the molar mass. What is the molar mass of hydrogen gas? Very simple. H is 1, so H2 would be 2. So it's 2 grams per mole. Multiply that out. 2 moles of hydrogen times 2 grams per mole gives us 4 grams of hydrogen gas product. It's a 2-step equation, right? This is the beginning of stoichiometry. Try another one. Here's what happens when we go to the dentist, right? Nitrous oxide, laughing gas, yeah? Comes together with the oxygen we breathe to form nitrogen dioxide. Very, very good. First of all, are we balanced here in our equation? We always start the same way. Let's see. 1N, 1N. Oxygen, 3, 2. That's not good. Let's go ahead. What if we take this up to 2? But now we got 2 nitrogens, so let's go ahead and put 2 nitrogens over here. 2 times 2 is 4, and that looks okay. I think I'm balanced. So the mole-to-mole ratios are 2 to 1, gives us 2. Very good. You always got to do that first, yeah? That's the recipe. Now, this one is a little tricky. Now, if you don't understand this problem, don't worry about it a whole bunch. This is a real extension of what we're doing. Everything I've told you so far is easy because we are assuming that only one thing is limiting, and I told you what that reactant is. In this problem, I'm not telling you which one is the reactant that is limited. Who determines how much product we get? Well, let's take a look. I have 240 grams of nitrous oxide, 64 grams of oxygen gas. Okay, so first of all, I need to determine, right, who is the limiting guy. Let's take a look here. Well, the first thing I could tell you is the molar mass of nitrous oxide. You should be able to figure that out. Very simple, right? 14 plus 16 is 30. So, if we have 240 grams and the molar mass of it is 30 grams per mole, that means that I should have 8 moles of nitrous oxide gas. How about the oxygen? We're saying that we have 64 grams of it, and the molar mass of oxygen is O2, is 32 grams per mole. Very good. 64 divided by 32 is 2. You can see I did numbers to make things a lot easier, right? Okay, so basically what you've got here is 8 moles of nitrous oxide, and you've got 2 moles of oxygen. Now if you just look at this ratio, even though it's 2 to 1, 8 to 2 is not 2 to 1. 8 to 2 is 4 to 1. So that tells me that I've got a lot more nitrous oxide than I need, and oxygen is the one who's limited. Okay, oxygen is limiting, so I don't care about this. So the amount of product will be determined by the amount of oxygen that I have. Let's go ahead and do it now. So that means I have 2 moles of oxygen, and we multiply it by the ratio. What's the ratio? You get 2NO. Oops, that's not 2NO. You get 2NO for every 1 mole, right? For every 1 mole of oxygen. So let's write that in there. 2 to 1. Okay, there we go. Let's do the math. 2 moles times the ratio 2 over 1 gives us 4 moles then of product, which is NO. And if I wanted to, I could take that even one more step here, right? By, oh, I'm sorry, it's not NO, it's NO2, right? Sorry about that. Let's put that in there, NO2, excuse me. If I want to, I could take it one more step by using the molar mass to convert that into grams. Now don't worry, that's a real tricky problem. I wouldn't hold you to something like that on a test, but if you understand it, you're really way ahead. Okay, so that's stoichiometry part 1. Next time, we'll put an additional step in there, and we'll talk about how to solve this using dimensional analysis.